time right now is 2:16 p.m. And then we're doing FRQ 6. So FRQ 6 asks you to find, so the first question asks you to find the speed of the object, and to know that we would have to find acceleration first. So I'm gonna break up my calculations into 3 parts for part A. It's gonna be the block, the pulley, and the spherical, the hollow sphere. So for the block, the mass 0.5 block is gonna be, the equation I'm gonna use for it is gonna be net force equals mass times acceleration. And we know that the forces acting on that block is going to be the force of gravity. And there's a tension, which is, I'm going to call this one tension right, and this is tension left. So since we know the block is moving downwards, it's accelerating down, gravity is greater. So it's going to be Fg minus tension right is going to equal Ma. And this can further be broken down, or actually we're going to rearrange it so that we can isolate for tension right. So that's going to be, we move tension right over here and Ma to the left side. So it's going to be tension right equals Mg minus Ma. And that's the equation we have for the falling mass. And then we're gonna do the spherical shell, this one. So we know that since this is a sphere, we're gonna use net torque equals inertia times alpha. So net torque equals inertia times alpha. And we know that torque equals tension times the radius of the sphere, which is a big R. And also inertia can further be broken down into C big M big R squared, because that's the mass and the radius of the sphere. And also alpha can be broken down into A over R. This means when we have all these definitions here separated, if we change that first formula, plug in all these definitions, we're gonna have, so the net torque on the sphere is only one torque. It's this tension here, which is tension L. So that's gonna be, since we know that that torque is tension times radius, that's gonna be tension L times radius of the sphere is equal, and we have here inertia can be broken down into CMR squared. So that's going to be C, mass of the sphere, radius of the sphere squared, times alpha, which we also know can be broken down into A over the radius of the sphere. And here we see that we can cancel R on both sides of the equation, because there's going to be, you cancel R on both sides of the equation. R here, and since that's 2 R's, this R squared is also going to be canceled. So simplified, that would put it at tension left equals C, mass of the sphere, times A of the system. And we know that the sphere is a hollow sphere, and so the constant or the coefficient of a hollow sphere is 2 over 3. We can put that here, which is going to be tension left equals 2 over 3 mass of the sphere times acceleration of the system. Now that we have those two, we're going to set up the equation for the pulley. And the pulley is probably the most important for the system calculations, because it ties the two calculations that we just made together. So we know that the pulley has 2 torques acting on it, which is the torque created by the tension left and the torque created by the tension right. So that's going to be, so using the net torque equals inertia times alpha. That can be broken down, since we know that the sphere or the pulley is going to be moving in this direction because the mass is falling this way. The torque right is going to be greater, and that's going to be torque right times the radius of the pulley minus torque left times the radius of the pulley. And that's going to equal, since this is given, since the inertia of the pulley is given as I, we're not going to break it down into cm r squared, which is going to leave it as I, and alpha can still be broken down into A over the radius of the pulley. So now that we have that, these two, we already created equations for torque right and torque left. Oh, also you can cancel out the r's on both sides of the equation. So we're going to be left with a simplified as torque right minus torque left equals IA. And now that we have that, we can just plug in actually, we're going to leave the r's here because we're not breaking down r's, so technically we can't cross it out. So it's going to still be torque right times r minus torque left times r equals IA over r. So we're going to leave the r's there actually. And then we're just going to plug in the torque right equation we found up here and the torque left that we have. So that's going to be mg minus ma, that's tension right times r, minus tension left, which is 2 over 3, capital MA, which is the small m is the mass of the falling block and the big M is the mass of the sphere. So we have that times the r of the pulley equals inertia of the pulley and A over r of the pulley. So all of these are given. So now all we have to do, we're going to be solving for A. So we'll just plug in what we know. So we know that the mass of the falling block is 0.5. Gravity is 9.8. Minus the mass of this block is again 0.5. And we have an A here that's unknown. And we have the radius of the pulley is 5 centimeters. And we know that 5 centimeters is equal to 0.05 meters. Since we're doing standard units, we're going to put in 0.05 meters. And then with the rest of this, minus 2 over 3, the capital M, which is the mass of the sphere, which is 5. And then we have an unknown A, and all of that multiplied again by the radius of the pulley, which is 0.05. Is equal to the inertia of the pulley, which is given to be 3 to the power of 10, or 3 times 10 to the power of negative 3. And then we have the A unknown value and the radius of the pulley, which is again 0.05. And now we have this equation that we're going to want to put in the calculator. So I'm going to plug all the numbers in. 0.5 times 9.8. And we see here that the radius is distributed to both these terms inside the equation. So it's going to be 0.5 times 9.8 times the radius, which is 0.05. Is going to be 0.245. So that's one of our terms. And now we're going to do this term, which is 0.5 times A, which is going to be variable. Again, the radius is distributed to both, so 0.5 times 0.05 is minus 0.025A. And then we're going to do this one, which is 2 over 3 times 5 times the variable A times the radius times 0.05, which is going to be 0.166A, which is our variable. And on the other side, it's going to be 3 times 10 to the power of negative 3, and divided by 0.05 is going to give us 0.06A. Now we have all our either constants and then a variable A. So we can move all the A's to this side so that we'll have all the variables on one side. So adding 0.025A and 0.166A to this side, we're going to have 0.245 left on the left side equals, so 0.025 plus 1, or 0.166 plus the 0.06. That's going to give us 0.251a. And to find for a, we're just gonna divide both sides by that number. So 0.245 divided by 0.251. Acceleration is gonna be, of the whole entire system, is gonna equal 0. So storage ran out on my last video, so I have to start on a new phone. But we're gonna pick up from where we left off, where we found a for the acceleration for part A to be 0.976. So we use our common formula. VF squared minus VI squared equals 2AX. And since we know that VI squared is 0, because the object has rest, that doesn't factor in, so VF squared equals 2, acceleration is 0.976, times the distance x that the object moves is 80 centimeters, which we know would be 0.8 meters, 0.8, and then that means the equation would be VF squared equals 1.56, square root that. We have VF equals 1.25 meters per second. So that's the answer for part A. And then, so part B, as for the time that it takes the block to fall. So we're going to use the equation x equals 1/2 AT squared plus VIT. So we know that that's going to be x is 0.8 and then equals 1/2. Our acceleration is 0.976 t squared. And since VI is 0, this doesn't factor in two ways, we can cross it out. So it's going to be 0.8 equals 0.976 times 0.5 is 0.488 t squared. You divide both sides by 0.488. It's going to be 0.8 divided by 0.488. Square root that. You're going to square root both sides. You get t equals 1.28 seconds. Alright, okay. So for part C, it's asking us to find the sphere's rotational kinetic energy. So we know that KE rotational, formula for KE rotational is 1/2 inertia times omega squared. And we can break that down into inertia. We know up here we already defined inertia as equaling CMR squared. And we know that omega is V over R. So that's going to be V over R. We're going to plug that in for omega squared. So it's going to be 1/2. Our C value for the sphere was 2/3. And then the mass was 5. And the radius, we can go ahead here. You can see that if you square this, it's going to be V squared over R squared. And those R's will cancel out. So all you need to do is plug in the 1/2 cm, which we have here, times the V squared. And we know that the V of the V when the cord has moved 80 centimeters is going to be the same as the V of the falling mass, because the system moves at the same speed. So it's going to also be 1.25, which is what we found up here, squared. So if you plug all that in, you have 0.5 times 2/3 times 5 times 1.25 squared. And you're going to get the KE rotational of the sphere is equal to 2.60 joules. And then we have space here. So for part D, we have what fraction of the total energy has been transferred to the pulley. So first, to find fractions, we need to find the total energy. And to find the total energy, we're going to use potential energy. So we know that the total energy has to equal the potential energy of the block initially. So the initial potential energy. So our KE total is equal to mgh initial of the falling mass. So we're going to plug in the values we know for the falling mass. Equals, the mass is 0.5, gravity is 9.8, and the initial height that from relative to where the block dropped would have been 0.8 meters. So 0.5 times 9.8 times 0.8 is 3.92. So KE total is 3.92 joules. So now we're going to find the kinetic energy of the pulley. So the kinetic energy of the pulley is equal, since the pulley is rotational, it's going to be 1/2 IW squared. So the kinetic energy of the pulley is like kinetic energy rotational. We can break that down into 1/2. And the inertia of the pulley is given, so we're going to leave it as I. And omega, we already said that it could be broken down into V over R. So V over R squared, V squared over R squared. So plugging in the numbers that we know, it's going to be 1/2. The inertia of the pulley is 3 times 10 to the negative 3 power times V, we know again, is 1.25 squared over R squared. R of the pulley is 0.05 squared. So if we plug that into a calculator, we get the kinetic energy of the pulley is equal to 0.5 times 3 times 10 to the power of negative 3 times 1.25 squared divided by 0.05 squared. The kinetic energy of the pulley is 0.9375. And to find a fraction, we're going to put KE pulley over KE total is equal to 0.9375 over 3.92. So the fraction that we end up with is so the kinetic energy of the pulley is 0.239 of the kinetic energy total.